Hey programmers, Alvin from CoderBay here. Welcome back to our crash course on data structures and algorithms. And this time around, what I want to do is show you all about combinations. So if you haven't already, I highly recommend you check out our previous videos on recursion because we're going to utilize those basics in this next lecture. But for now, what is our objective for today? Well, what I want to do in the long run is have us implement some code that generates all possible combinations. And of course, along the way, I really want to make sure we have a great visual understanding of how to actually generate combinations. So let's start by going over some background information. What we're starting to do in this lecture is actually explore the field of combinatorics. So if you're familiar with some math, combinatorics is really just the field that's concerned with counting things. Combinatorics is a really great topic to familiarize yourself with because it's a pretty common one when it comes to coding challenges and interview-style algorithm questions. Combinatorics is actually a fairly large topic that if we master, we can actually solve a lot of different style problems. Some common questions that we will be able to answer include things like, given n things, in how many ways can we arrange them? In how many ways can we do x? Or other questions like, what is the shortest way to do y? And I won't be covering how to implement all of these sort of algorithms right now, but we'll kind of start to dive into this field of combinatorics. That means our first stopping point will be about generating just combinations, right? So what is a combination? You've probably heard of this word before, maybe just used informally in English, but let's actually give it a really nice, well-defined meaning. For us, we're going to define a combination as a collection of items where the order among those items does not matter. And this is going to be the key defining characteristic of a combination, right? The order among the items does not matter. So for example, let's say I gave you an initial set of items A, B, and C. What are all possible combinations we can generate would actually be these 8 combinations. The first thing you'll notice is technically if we don't grab any elements from this master set of 3 things, we could just generate the empty combination containing 0 elements. And we have all other combinations, right? We have just a single element over here. We have all pairs of elements. There's actually only one triplet that we can ever take. The important thing to understand is, again, a combination is a collection of things where the order does not matter. For example, notice here that we list a combination of AB. That means we also don't have to list BA, right? Because I don't want to duplicate any combinations if I just switch around their order, right? That really doesn't count as a new combination. What you'll also notice about this list of combinations is that it's complete, meaning that we have all combinations of all possible lengths, right? If you're familiar with some math, you may have heard of things like 3 choose 2, which means that you're really referring to only the combinations of length 2. But for us right now, we're trying to generate all possible combinations of any length, including the empty combination. So here's some food for thought. As my set of initial items grows larger and larger, it will be the case that, of course, the combinations also increases in number. And in a very general sense, if you're given a set of n things, they're going to be exactly 2 to the n possible combinations. What I want to do is really make sure we understand why there are actually 2 to the n, right? So a few things I'll kind of keep in mind is, why does it tend to give us like an exponential number of combinations, and why is the base of that exponent 2, right? We need to really find the meaning behind this number. That way we can actually implement this algorithm later on. But for now, let's head to a nice little drawing. So here I have a sketch of how we can actually generate all possible combinations. What I want you to bear in mind right now is that we're kind of assuming in this little illustration that our original set of items is just A, B, and C, right? So that's really the set of items that I'm choosing from. And so how can you actually interpret this diagram? Well, the first thing you'll notice is it kind of describes a tree, right? Looking at the very top of this tree, we actually have the empty combination. And what you'll notice is along the side of this tree, kind of at every level of the tree, I kind of denote a different item, right? Here I have A, here I have B, here I have C. And what I'm showing you is at every level of this tree, we make a decision about the current element. In other words, if you're trying to generate a combination from scratch, you probably start with an empty combination. And then from there, you make a decision about the item A. And what is that decision? Well, there are 2 options. For this item A, you can either not take the A, in which case your combination still is empty, or you can actually take the A and include it into your current combination, which means that your combination just has one A in it right now, right? So the pattern to recognize in this visual tree is from one node to the next, if I take a left-hand edge, that means I'm excluding the current element. If I take a right-hand edge, that means I'm including the current element, right? Cool. So from here, I already made my decision about A, which means if I go to the next level of the tree, I'm making a decision about B. And the decision has really the same format, right? Let's say my current combination is the empty one. If I go left, that means I don't take B, so I stay empty over here. If I go right, that means I include B, which means my combination I'm currently generating just has a lone B. And things get a little more interesting on the right-hand side, right? Again, from this combination that only contains A, if I go left, that means I am excluding B. So I still just have A remaining. But if I go to the right, that means I'm actually taking B. So now I have a combination of A and B. And of course, you can see the same pattern take place at the very final level over here, right? Whenever I go left, that means I don't add C. When I go right, that means I actually add C into my set. So just honing in on, let's say, this little subtree over here. I have my original collection of A and B. And when I don't take C to the left, I still have A and B. But if I take C, then my new combination is just A, B, C. What you'll notice is at the very bottom of this tree in green, I actually have all possible combinations, right? I have the empty combination, I have all the combinations of just single items, I have all pairs, and I also have the lone triplet that's possible over here, right? So what does this tree describe? Overall, it kind of denotes the decision process we make as we generate all possible combinations. What I really want you to understand about this decision process is that it's binary, meaning every decision I make has two possible outcomes, right? And that's exactly why I get sort of the base of 2 in my exponential number of combinations, right? As I go from one level of this tree to another level, I'm always just doubling the number of nodes, right? I have one node here on this level, 2 nodes on this level, 4 nodes on this level, and then 8 nodes at the very bottom, which exactly describes why there are 2 to the 3, or in other words, 8 different combinations for the elements A, B, and C. So that's our conceptual understanding for how to generate combinations. Let's actually implement this process in some code. All right, so here I am in my text editor. Let me go ahead and start defining my combinations function. And it's going to take in a set of things. We'll kind of just take that in as an array. We'll just call it elements. And what I want to do is have this function return all possible combinations from those elements. So for example, if I called this function combinations and I passed in, let's say, an array of exactly what I did in our little sketch, right? So it was just A, B, and C. What I should be getting back is a 2D array. I should be getting a 2D array of this shape, right, where every subarray represents one of the combinations, right? In this particular example, the array I get back should have 8 different subarrays, where each of them represents a unique combination. Cool. So with that in mind, how can we actually tackle this problem? Really, the most probably straightforward way we can implement combinations is actually recursively. And because we did such a nice drawing in understanding how to generate combinations just using our decision process, it's actually not too crazy in the code. So since I've decided to tackle this one recursively, let me think about a base case. Like we said in our previous lecture on recursion, when it comes to the base case, what we should do is think about the smallest case of the input where we kind of just automatically know the answer. In other words, if I gave you an array of some elements to kind of generate combinations from, what would be the simplest input array I can give you? Well, I think the simplest input array would actually be just the empty array, right? What if someone asked you to generate all possible combinations and there actually wasn't even any items to begin with? Well, in my eyes, there's actually just one combination you can ever generate, and that would actually be the lone empty combination. So an important thing to know with the structure of this problem, right? In general, I want my combinations function to return an array of all of the combinations, right? You'll notice that if we're passed in an empty array, I think it logically makes sense for us to return a kind of 2D empty array, because this inner subarray represents the empty combination, right? If we had just returned an array that looks like this, that would kind of mean that there are no combinations at all, not even including the empty combination, right? So I'm going to consider this some valid output for the case where I'm given an empty set of elements, right? There's only one combination you can possibly generate. That is the empty combination. And we're just throwing that in another array to return, right? And that makes it nice and consistent compared to when we actually have some elements to deal with, right? So let me start with that as my base case. So I'll go ahead and check, hey, if the elements I'm given is actually empty, so if the length of that elements array is 0, then I ought to return my combinations that only include the empty combination, right? So here I have my empty 2D array. cool. So that's a nice base case scenario. But then how can I generate my recursive case, right? And here things get a little bit tricky, right? What I want to do is really think about the process I took in my diagram, right? So the key concept in that diagram was I kind of had one of two options, right? I can either take the current element or I can not take the current element. And I know that in the long run, if I want to have this base case eventually be hit, then I need to shrink the length of my elements array. So here's what I'll do. Let me split this up into some different variables. Let me grab the first element of my array. So I'll say const, we'll say first L, and I'll say elements at index 0. I'll just start with a nice baseline solution over here. So now that I'm grabbing the first element of this array, I'm going to kind of say that this first element is the one I'm making the decision for, right? So for this first element, I can either not take this element or I can take this element. So here's what I'll do. Let me actually generate the rest of the elements. So what I'll say is rest equals elements.slice, and I'll slice starting at index 1 all the way through the end. So just to quickly go over this pattern, right? Probably seen this before, but if you're just hopping into this lecture out of the blue, in JavaScript, slice just gives you a subarray, right? So if I had an array like this, and I do array.slice, starting at index 1, that gives me elements in that subarray all the way through the end, so B and C over there, right? So here I've separated the first element from the rest of the elements. And what I'll do to start is actually generate combinations on just the rest of the elements. So there are a few things you should notice about this recursive call. If I do a quick spot check, this recursive call is kind of in great shape because I definitely shrunk the length of my array that I'm passing in by one element, right? It's going to be one element shorter. So that means it's making some great progress toward this base case. And if I think about like what will happen like recursively here, if I pass in only the rest of the elements into combinations, then the 2D array I get back from this call over here shouldn't even contain, let's say, the A element at all. It shouldn't contain the first element at all. Right? At any point in time, when you're coding recursively, you always assume that you get valid output, right? So if I'm calling combinations, I assume that it gives back a 2D array of all of those combinations. So let me save that to a variable, and I'll try to be very like literal here. That way I don't have to comment the code. So if I make this call, what I'm getting over here is, we'll say combinations, I'll say coms without first, right? So in this return value for combinations on the rest of the elements of the array, it's guaranteed that none of those combinations contain the first element because I didn't even pass the first element down to that call, right? Cool. So from there, I have all the combinations without the first element. Now I need to generate the combinations with the first element, right? Remember that in our diagram, we talked about that sort of duality, right? I have a binary decision process. You either take the thing or you don't take the thing. So let me actually write the logic that takes the thing. So I'll create a nice variable here. We'll just say coms with first, kind of having some nice symmetry here. And I'll actually generate that by utilizing this value. So I'll start this as like an empty array maybe. And what I'll do is I can take every combination without the first element. So I'm going to iterate through this collection. So let's do coms without first. And here in JavaScript, I'll just use a for each. You can just use any loop that'll iterate through every element of this array. And for every single combination, I'll do some code. So now that I'm referencing this single combination, what do I want to do with it? Well, the important thing to understand right now is this combination, this com right now, does not contain the first element that I have referenced over here. So what I want to do is create a copy of this combination. A nice trick I can do in JavaScript is to actually create a literal array, and I can spread out the elements of that original array. And to that array, I actually just want to insert my first element that I have referenced at the top of this function. So I'll insert basically this first element. So again, really the logic of this code is just saying create a copy of combination, and then in addition to it, also add on the first element. So I'll just save that as my single com with first. So I just want to follow some nice symmetry here. This single combination, notice that it's singular, it says com and not coms. I'm eventually going to just add this single combination into my collection of all combinations, right? But let's just go over this pattern. Maybe you're kind of following this lecture, but not going to implement this in JavaScript. All I'm doing is creating a copy over here, right? So let's say I have my nice array of things. And what I can do is, let's say, create a new array where I can just like spread out the elements of the original array. So that gives me a nice copy of this array. And the great thing is it's a unique array in memory, right? So I don't have any like duplicate memory references. But really the full trick I'm using here is also adding an additional element. So if I look at my new array right now, here it is. If I do something like square brackets and I say spread out the elements of that new array, it will have all of those original elements, but then I can also add on anything I want, like a z, right? So I'm really just creating a copy of this combination while also adding one additional element. Cool. Like I said, what I want to do is take this combination, which definitely contains the first element, and I want to add it to my kind of master list over here. So I'll just say coms with first dot push. I'll push this single combination. If you'd like, you can probably forego this variable. I'll kind of keep it in here just for some explicit clarity. Cool, so let's kind of break down what's happened so far, right? So we started out by making a recursive call on the array that does not contain the first element, right? So that will basically magically recursively give us all the combinations that don't have the first element. And then from there, I also need to generate all the elements with the first element, which means all I have to do is just take those elements or those combinations that did not have the first element and just add the first element to them. And then from there, to return my final answer, it's just a matter of returning both of these things combined, right? So using that trick again of spreading things out, I'll return a new array where I take all of my combinations without the first element and also add my combinations with the first element. So it should be without and with over here. If you wanted to, and if you're dealing with another language, all I'm doing here is really just concatenating two arrays together. So let's give this code a shot. Let me console.log our test cases over here. So we're trying two things. We're trying the ABC and also the empty array. Let's give this a go. Nice, and there we have all of our combinations. So doing a double check of our very first result over here, that should be 8 unique combinations, and it is indeed 8 combinations. And for the empty array, I just have my lone empty combination. This is pretty great too, because this should be generalized for all possible, test cases. So let's say I just gave AB. If you think about all of the combinations of just AB, according to our little formula, that would be 2 to the n, in other words, 2 to the 2, so just 4 combinations. Let's make sure we get 4 combinations over here for AB. Nice, there I have my 4 combinations, the empty, the B, the A, and the BA combined. So I know what you're thinking, right? How did this code actually work, right? Really, the heavy lifting we did was all about making that drawing and tracing through it earlier, right? All we did was really take that drawing and translate it into some code. But let's say I kind of wrote 2 examples that really show you what happens here, right? So imagine that we're just calling combinations on ABC. So we know that we get all possible combinations. Let me save this file, right? And we know basically on like the first call that we make, technically this function call would make another recursive call to just BC, right? So let's kind of see what that would yield. So if I try these 2 combined, if I just made a recursive call to BC, I would get back this array of combinations, right? Because remember that in our code, we say we kind of reserve the first element. So that means we're reserving the A, and when we grab the rest of the elements, rest refers to this BC array, right? Really this array over here. And we know apparently that when we call the combinations on just the BC array, that would be this line over here, we get back this array of 4 things, right? What you'll notice is those 4 combinations definitely don't contain A, because that's how I kind of designed the code over here. I don't pass an A along that recursive call. And to generate kind of the symmetry of all of the combinations that also include A, all we need to do is take this list and insert A into each of them, right? If I insert A into this combination, that gives you the lone A. There it is. If you insert A into this one, you get CA, which is this one over here. If you insert A into this one, you get BA, which is over here. And if you insert A into this one, you get our triplet CBA over here, right? But in addition to that, what you also should do is include these combinations themselves, right? So this is 4 combinations. And then we also, in addition to it, add A into each of them. That would just double the number of combinations, right? So before we say farewell to combinations, let's do a nice analysis of this implementation. So I think this is probably my go-to implementation for combinations. It's not, let's say, like the fastest implementation of combinations, but I think it's one that's very easy to explain during an interview, as also one that is easy to kind of visualize, right? It's really easy to draw out and really understand the process. So if we start by just describing the time complexity, you can probably guess that the time complexity is, I guess, at least going to be 2 to the n, because there are like 2 to the n results we need to generate. And you'd actually be right if you kind of just made that guess, right? The number of iterations we're going to do across all of our recursive calls is really 2 to the n, because we get that doubling nature, right? From one recursive call to the next, I actually double the size of this array, right? You can see that I take my original elements and sort of double them over here. And in a similar way, how can we describe the space complexity? Well, we'll need to think about a few things, right? Starting with just the number of recursive calls on our call stack, right? The stack depth that we used. If you look at how the recursive case relates to the base case, at any point in time from one recursive call to the next, we're shrinking the size of the array by exactly one element. Because again, rest does not include the first element, right? So that would give us at least n stack frames, right? So if that gives us n stack frames, then we just have to, in addition to that, consider any work we do within each stack frame, or really any additional space we consume for the space complexity, right, for each stack frame. We know that there are n stack frames, and each stack frame is going to contain an array of, at worst, n elements, right? They're really going to be like n minus 1 elements. So actually, I would have n times n space complexity if you consider the stack frames and also the additional arrays you create within those stack frames, which overall gives us an n squared space complexity. So there you have it. We implemented combinations together, right? Key things I want you to take away now from this lesson is, given n things, there are 2 to the n possible combinations, and you'll definitely want to really understand the tree visualization, right? Really understand that when you generate combinations, you're making that binary decision process, which is why I have 2 to the n in the base of that exponent. So now I turn it over to you. What you'll want to do is head down to the link in the description, where we have some links to CoderByte where you can actually practice some problems that utilize this combinations logic. In the next video, we'll actually go over a very similar topic in the field of combinatorics, which would be permutations. So stay tuned for that.